Three point charges are arranged at the corner of a square of side L as shown in the figure. We have two parts to the problem. In part A, we are to find the potential at the fourth corner while taking as a reference v equals 0 at a great distance. And in part B, we are asked that if a particular charge were to be placed at this corner and then released, what would be that charge's velocity after moving a great distance? This problem would be extremely tedious if we were asked to calculate electric field at the point A. However, we are asked instead to calculate electric potential. The significant difference between field and potential is that electric potential is a scalar quantity, and so we simply add amounts and we don't have to account for directions. We're going to begin by recognizing that there are three contributions to the electric potential at point A, and all three of these are point charge contributions, where the formula for the potential due to a point charge is kq over the distance r. In this case, given the fact that we have 3 point charges that contribute, the total potential at the point A will be the sum of three terms, kq1 over r1, kq2 over r2, and kq3 over r3. If we look more closely at the figure, we can find that the distances r1 is here, r2 is along the diagonal of our square, and r3, like r1, is along a side of the square. We'll be able to use the Pythagorean theorem, taking advantage of this right triangle, to note that r2 will be equal to the square root of L squared plus L squared, which simplifies to square root of 2 times L. In this case, the formula for the total electric potential at point A becomes K3Q over L plus KQ over square root 2L minus K2Q over L. Combining these terms, we have the simplified result of 1.707 KQ over L. In part B of the problem, we've been asked to consider the possibility that a point charge of strength plus 4Q has been placed at the location A. This charge is then released, and it will be repelled and fly off towards infinity. We are then asked to determine the velocity at this later point. We recognize that this problem is an exercise in conservation of energy, and all energy problems follow exactly the techniques we learned in first semester physics. That is, we define two moments, moment 1 and moment 2, and we set the total energy at moment 1 equal to the total energy at moment 2. The big change as compared to first semester physics is simply that we now have 5 forms of energy to consider at each of the two moments. Looking at moment 1, we see that there is no translational kinetic energy, no rotational kinetic energy, no gravitational potential energy, and no spring potential energy. However, we certainly have electric potential energy at moment 1, and therefore we take the amount of charge in question, that's the charge little q, times the voltage at the place where we put this charge, and that is the potential energy at moment 1. At moment 2, we certainly have translational kinetic energy. However, the other forms of energy are all 0. At this point, a bright student might want to stop me in my tracks, because that student would recognize that in order to construct a configuration of 4 total charges, I have to account for the energy necessary to place each and every one of those 4 charges there. And that energy should be in the total on each side of the equation. Well, in fact, if I put it on each side of this equation, that total, whatever it is, will cancel, and I'm just not going to bother to calculate it. We're now in a position to substitute in the fact that the test charge itself is 4Q, and the potential at its location was calculated in part A, yielding the expression shown here. Solving for V2 squared produces the result 13.65 KQ squared over LM, and after we take the square root, we'll have the result 3.7Q times the square root of K over LM. And this completes our calculation, not only determining the potential of an interesting configuration of several point charges, but also using the value of that potential to determine potential energy and applying that term to a conservation of energy problem.